Okay, welcome back. So now we are going to expand on what we did in the last video, and we're going to look at a different type of instruction format. In particular, more specifically, we're going to look at an I-type instruction. Okay, you will see that the data path, when we trace out how the processor works and supports these types of instructions, right, it's going to look a little bit different. Okay, and I'll point that out, some of the key differences once we see them. A lot of stuff looks really similar. So it also gives us an opportunity to rehash some of the things from the prior video to kind of make them lock in a little bit, the stuff that's similar, as well as point out things that are new and different. Okay, so first of all, we need to talk, again, just like the last video, we got to point out some things about the state of our system to be able to make sense of how the tracing is going to work, okay? Because we have some things that we have to assume are already being stored in the registers or in instruction memory to be able to properly trace this. Okay, we're going to trace this instruction down here. It's an add immediate instruction, okay, aka an I-type instruction, okay, I for immediate. And we're look at this, we're going to take register 4, and we're going to add it to the immediate value 15. Okay, so register 4, this is really the only thing we need to know about the current state of memory here for the register file is this, because we're going to go ahead and we're going to read this location. Okay, we don't really necessarily need to know the other values. We actually don't need to know those. Okay, but we are going to read that. We do need to know that particular register. Okay, the other thing we need to know is, because just like last time, that this is our instruction memory here. Okay, I need to know the address that's stored in an instruction memory. I need to know that because the program counter, if we're tracing this properly and we're trying to make it complete, the program counter is going to point, right, is basically a pointer that's storing the value of that address. It says, hey, that's the address that we're going to need to read from. Okay. And then here, obviously, we have the machine code for it. All right, so let's trace this instruction, and then just to recap, this is the instruction we're tracing. We're tracing an add immediate, and I think it was, yes, register 3 here is going to get the value of register 4 and the immediate value 15. Okay, so we'll write that down so we kind of have that in the back of our minds here, right? And we could start in a couple different places, but we could start here looking at that from the perspective of looking at what's coming out of the instruction memory here, okay? And we know that just like last time, what we're feeding into the control unit here is the opcode. Okay, if we look at the opcode here, it's going to be 1001, 1001. 0001, and then I think it was just 0000. Okay, now I want to point something out. Okay, I want to point something out that is actually 10 bits, right? But here it's showing that it should be 11. Okay, it's because bit 21 is actually a do not care. Okay, in this case, it's going to indicate the same thing. We don't need to actually know that bit to know that this is an add immediate instruction. Okay. Bit 21, in fact, is going to be used down here as we're going to use part of it. It's coming through what's referred to as the sign extender. Okay. So we're going to run this down through here. Okay. And this is going to contain our immediate field 15. Okay, and we're going to stick with being a version of the ARM processor that's a 32-bit architecture. Okay, so I'm going to change this diagram a little bit to make it a little bit more realistic for our purposes. That the bits that we're really concerned about here are not bits 31 through 0, the entire thing, but instead really bits. What is this? So we're starting at, this would be 0 to 9, so it's bits 10, and I think we go to, it's to 21. Okay, this bits 10 to 21. is really what I care about. So I'm just modifying this slightly. Okay, because this is really bits 21 through 10. Okay. All right, so those 12 bits, and we take these 12 bits and we turn them into 32 bits. Okay, without changing the value. That's the point of the sign extender. So I just want to kind of reinforce that a little bit. What the sign extender is doing, okay, is if we have a value such as, if we look at like 1 byte, this is 15, right, in base 10. Okay. Let's assume actually that, let me make this, let's make this a little bit more similar to what we saw in the last, in reality, we were saying with the sign extender that there's 12 bits here. What the sign extender does is if this most significant bit here, remember, if that bit all the way to the left, that most significant bit, if it's 0, it indicates that the number is positive. Okay. If it's 1, it refers to it that it's a negative number. Okay. The sign extender just takes whatever that most significant bit is and runs it all the way to the end, right? So we have a 12-bit number like this. Okay. The sign extender is going to turn that into a 32-bit value. Okay. It's going to turn it into 32 bits. Okay. And if it was a negative number, right, you would have some sort of leading 1. Right? This would indicate that it's a negative number. Right? The sign extender is going to do the same thing, except now it's going to be all leading 1s. Right? This way it does not, that has the effect of not changing the value of, right, to make it more bits without actually changing the value of anything. Okay. So that's all it does, right? It's going to take a 12-bit number, turn it into a 32-bit number without changing the value. Okay. And the reason for that, we're going to see in a moment, right, is because the ALU works on 32-bit inputs, right? So it has to be 32 bits. It has to be 32 bits. Okay. So we can go ahead. We could write that in here. So it's not changing the value at all. So it's still 15, and it's 15 here. Okay. Now, how did I get to this, right? Let's just kind of point out a couple things, right? This is the immediate field, the 15, right? I know that that 15 is going to be added to the value in register 4, right? So 15 comes through here and gets fed into the ALU, right? Remember, we only read, in this case, we only read 1 register, okay? We only read 1 register. We do not care what's read out of the second register output here. We can read 2 registers at a time. The processor supports that. The processor supports reading 2 registers in parallel. Okay. However, right, we don't actually need that. We actually don't need to be able to do that, right, for this type of instruction. For an immediate instruction, because we're using that immediate field. We don't need that second register that's being read. Okay. All right. So here, bits 9 through 15, bits 9 through 15, that should be our register 4. If we come back over here, we should see that, right? We look here, we see our register that we want to read from, right? Our register 4, right? Bits 5 through 9. I think I said that correctly. I'm not 100% sure I did, but it's bits 5 through 9 is register 4, right? We read register 4, right? And we put the value of register 4 here. Okay, the value of register 4 is this, which looks like that's 8. All right, 8. Okay. We're going to have 8 plus 15, but we can come back to that. All right. So we also are writing to a register. Okay. We are going to write to register 3, right? We're going to write to register 3, right? This should be register 3. Bits 0 through 4. Bits 0 through 4 is register 3. Okay. I did mention in an earlier video that we get a sense of why the destination register is put in this different position here, a little bit out of order than what you write it in ARM assembly, right? And we can actually kind of see that now, that we grab those bits that are over here, right? Those are the ones that we're grabbing and feeding in here, okay? And there's times where we want to grab those and feed those in up here, but we'll look at that at a later date. Okay. So we've done that. Right now, let's add our 15 and 8. Okay, so we get our 23. We're going to bypass memory again, and we're going to write that 23 all the way back. Okay. We're going to write that all the way back into the write data port into the register file, right? Effectively what we're doing, right, is we're writing 23 to register 3. Okay, so let's go ahead and let's write that. We've got 16. Okay. Plus 4 is 20. Okay. 23. It should be right. Okay. 23. Okay, we're writing that back here. Okay. All right, so we're getting close to done. I'm going to do the control signals last, right? I want to just point out a couple things, right? We have like a do not care here. We don't care what this value is there. Okay, same with here. It's coming into that multiplexer. We don't care. Doesn't matter because we're not going to use that data. Okay, we don't care here either of what's coming out of memory because we're not going to use whatever's coming out of that location. So we technically read address 23 in this case, right? Actually, we don't have the control signals tells us not to read memory, but regardless, any sort of junk or noise that's on that signal here doesn't matter. Okay, because we're not going to read it. Now let's just take a step back. We're close. Let's look at what we're gonna have to advance the program counter by 4, right? We said that this instruction here is in this memory location. I think it looks like location 16. Okay, so we're gonna say, okay, it's in location 16. That's the address we read. We're gonna advance that by 4. Okay. So that the processor is able to advance to run the next instruction at the next clock cycle. Okay, at the next clock cycle, it's going to advance. It's going to then go and run the next instruction because we've now moved the program counter value up by 1. It will change at the next clock cycle. Okay. All right, so let's just wrap this up then. Let's just look at the control values, right? Like I said, it's good. Like you can look up what the control values are for different types of instructions. However, it's a really good idea to be able to derive them based on what the instruction's doing. Let's make a good understanding of the actual, of what it must be and how a processor actually works, right? And how it's designed. If we look at this value here, the reg to location signal. Okay, that one's kind of unique because we're not using the output of that. We actually don't care what that is. Okay, doesn't matter. All right, I'm just going to run through and do these in order. Unconditional branch, kind of an easy one. Is the instruction an unconditional branch? No, it's not, so it's 0. Is it a conditional branch? Okay, nope, it's not that either, so it's a 0. Okay, we don't care about this signal. We'll see more on that later on. What that is, I don't want to explain it now because it'll just be confusing. Okay, but a 0 ANDed with anything is 0. 0 ORed with 0 is 0. Right, so we see how we got that. Okay. Then we say, are we reading from memory? No, we're not reading from memory. Right, the only time we're going to read from memory is in a load instruction. Okay. We have this signal here. This control signal controls this multiplexer. We selected location 0, which is indicating that we're bypassing memory. We're using the output of the ALU to determine what's written back to the register file. Okay. ALU op, right? I'm going to kind of skip the details again on that, but just indicate that this ALU op is setting a couple bits, once again indicating that we are adding, that the ALU should be doing an add operation. Okay. The mem write, are we writing to memory? No, we are not. So that's 0. ALU source, this multiplexer is selecting value 1. This is one of those things that is different. This is a key difference between the R-type and I-type instructions. Okay, is we need to select the immediate value, the 15, right? Unlike the R-type that would have grabbed that value from the register. So it's a key difference here. Just like we had also another key difference is that we don't care about the read register 2 because we don't actually use the output. Okay, so it's a key thing. Register write, are we writing to a register? Yes, so it's a 1. Of course we're writing to a register. We need the result of this to be in register 3 to be updated. Okay. All right, so we'll look at other types of instructions as well. We haven't looked at the data transfer instructions yet, so let's make sure that we do one of those. But once again, that's for another video. We'll follow up on that, and then we're getting closer and closer to be looking at a more realistic version of this, to be doing some parallelization and making this a faster, more realistic processor.